Hello everybody, welcome to the first webinar in this new series, the 2016 IEA Online Statistics Summer School. Let me start by introducing myself. My name is Lucy Shedden. I'm in charge of training and capacity building here at the International Energy Agency. I'm here with my colleague Klaus Petersen.
Yes, hello, I'm Klaus Petersen. I'm from the energy statistics in the non-member sections of the IEA.
And we had over 250 people registered for the session today. I see people are coming in bit by bit. We'll get started with a small introduction and then move on a little bit more as people come in a few minutes late. We want to thank you very much for all joining us today. It's such a pleasure to see such strong attendance for this kind of session and for the first that we're holding online. As you'll see from our website, this session is the first in a 4-week program during which we'll be taking you through some of the fundamental aspects of data collection, validation and use. The sessions will be taking place every Wednesday afternoon throughout the month of July. On the 13th of July, so next week, the session will be focusing on refinery balances. On the 20th, so the week after, on same time at 3 o'clock, there'll be an introduction to electricity and renewable energy statistics. And finally, on the 27th of July, the webinar will provide a high-level overview on energy balances. However, today, Klaus and I will be taking you through some of the essential elements of energy statistics, the fundamentals. This is what we've deemed to be some of the fundamental information required for dealing with data in the energy sector. Of course, given the complexity of the subject, there are so many things to choose from. So for time, we've had to be selective. However, our main goal is to really bring you back to basics, teaching you, or in some cases, reminding you of very important elementary aspects of this field of study. We have outlined on the screen here some of the main learning outcomes for this webinar and what we hope that you'll all achieve and take out of this. We will be beginning with a brief introduction on the importance of energy data statistics, data quality, and discussing some of the main issues that you may face when dealing with energy statistics and data. We will then move on to some of the basic concepts with an overview of the supply and demand breakdown, then moving into some of the basic conversions, then on to calorific values and explaining weighted averages in more detail. We expect the presentation to last about 30 minutes, and then we will have a 30-minute interactive session to answer your questions directly. You will see in the right-hand side panel of your screen, for those who may be less familiar with the equipment, is a chat option. This is where you can directly ask us your questions. Please write questions as the presentation is going along. We'll be dealing with them. If there's anything important that you want to ask during one of the slides, we will try and stop our presentation to answer this for you. So please don't hesitate. And at the end, we will try and filter all your questions. If for whatever reason, if for time constraints, we are unable to answer all of your queries, we will be making a document available online after this session with all the questions that were raised and answers. Also, this presentation we made online, a recorded version of this we made online for you all to see afterwards and to consult. If there's any queries at all linked to this webinar, please do not hesitate to email me at any time. My email is the one available on the website. So, without no further ado, we'll move on to starting with some of the most basics. As we've noticed from the registrations coming in today that there is a very diverse number of people interested in fundamentals of energy statistics and energy data. And that really raises the question of who needs energy data, why it's important. The answer is almost everyone and everywhere. There's a whole variety of issues and topics on which it is important. Here we have listed some of the main actors for whom energy data is important, starting with the macro level through to the macro level. Start with the rather rudimentary monitoring of utility bills within households up to the main decision makers at local, national and international levels to carry out their work. We will be coming to this in more detail, but I just wanted to also point out that there are, of course, a multitude of other actors who require solid, consistent and reliable data for effective monitoring of work and for research. For example, companies for monitoring loss as well as ensuring that they keep track of their environmental profile, academia for research purposes, and commodity traders who primarily and principally can use their data in order to better see how supply and demand is developing as they are trying to predict oil prices. As mentioned, energy data provides the basis for any sound energy policy, and therefore they are fundamental right along the policy cycle, from problem definition to agenda setting, policy formulation, implementation, and through to the monitoring and evaluation phase. This obviously, as we know, goes in through a through cycle, which I'll explain more now. From the point of problem definition, strong evidence is always required to corroborate the arguments. Without reliable energy data, evidence-based arguments are lacking, and defining the problem can be problematic. Data can help to set goals and targets, which in turn can strongly improve the possibilities that a policy issue makes it onto the agenda. Furthermore, when defining targets for a new policy area, data are important for preliminary analysis of what might and can work within a particular jurisdiction or country. The access to reliable energy data is essential in our efforts to avoid policy failure as well. Absence of such information can make the policy-making process extremely challenging, and decisions can, as a result, often be misinformed. The implementation process is also in need of consistent and reliable data. They can help us to set performance indicators, put in place a strong monitoring process, and implement evaluations. Data retrieved from any monitoring process can be used to support advocacy efforts, as they show whether or not we are making progress and if a project is working efficiently. This in turn, of course, can guide the development of new timely and relevant policies, which is my point at the beginning of the fact that there is a cycle going round, and where data is extremely important from the beginning through to the end and back through again. A great example of this on the energy world is energy efficiency policies. Reliable, timely and detailed data on energy end uses, markets, technologies and efficiency opportunities in all sectors contribute to the development of effective energy efficiency strategies and policies.
Hello everybody. I will talk a little bit about now what are good data. Lucy said that policymakers, they need good data. But it may seem like a very simple question to ask ourselves, what are good data? But it's good to remind ourselves what good data actually are. First of all, the policymakers Lucy was talking about want relevant data. Data should cover the policy area you're looking at. If you're looking at global warming, you need data on combustion of all fuels. Second, data should be reliable. The data should indicate the right level and the right developments from year to year. The third criteria is that data should be published within a reasonable time after the reference period. Most countries have already published summarized data on 2015. Lucy will soon talk about the supply and demand side of the energy market. Usually, supply-side data are published earlier than demand-side data. As you will see, there are fewer agents on the supply side, and the supply side is more regulated than the demand side. Last, but not the least, data should not be too expensive to collect. This is relevant both for the data collectors in the Statistical Office or the energy authorities, but also for the businesses who are obliged to report their energy production or their energy consumption. Businesses should not be imposed an unnecessary response burden. Several international organizations have done extensive work on what makes statistics good statistics. The United Nations have developed a set of fundamental principles for official statistics. You can see the statistics on this link. This is a one-page document on the very fundamental principles of data quality. The Statistical Office of the European Union, Eurostat, have elaborated further on these principles and added a few to come up with 15 principles for good data. And you can see here on this link which would come on the screen in a little while. It takes a little time, don't worry. The most important thing to notice is here that the Eurostat principles are much more elaborated than the United Nations. And each principle has a few indicators to check how a country is doing under each principle. For example, Principle 11 on relevance. In order to see if the statistics meet the needs of the users, there should be processes in place to consult the users. In other words, you should ask the users what do they actually want data on. And priority should be given to meet the needs of the users. Finally, when you're giving the users what they want, user satisfaction should be monitored on a regular basis through user surveys. But what can you do as a data analyst or a data producer? What can you do to make the data you're working with better? Well, the first thing you can do is that do you actually really understand the source data that you're working with? Understanding source data, how are data collected? Is it a sample or does it cover the whole population? It's obligatory to report data or is it voluntary to contribute? Is it official statistics or what is the nature of the data? Is it a trustworthy source or is it something that you should be a little bit critical towards? The second thing is that in order to understand data, it's important that you can explain trends over time. If you see that you have a timeline with 10, 20 years, and you can see that it goes up and down, it's important to understand the main reasons, for example, political changes in political policies to see what is actually causing the changes. And as a little hint, no matter how data are collected, it's useful to know somebody who you can ask technical questions. Somebody in the statistical office who is dealing with this, who can ask your very questions that can be very basic, but it can be very difficult to read sometimes. So, challenges in energy statistics. We do have some challenges, people who produce energy statistics. One of the biggest challenges that's happening at the moment in Europe, in North America, and in Africa, South America, in Asia, is the liberalization of the energy markets. In the good old days, there used to be one provider of electricity, one distributor of electricity. Now there are hundreds of players on the market. It's difficult to get information from all of these. And all these players are in competition with each other, so they are reluctant to reveal their data. They want their data to be confidential. At the same time, as the people in the statistical office are struggling with this, more work is passed on to the statistical offices. They should make data, collect data on renewables, energy efficiency, environment, and in general monitor policies which are becoming more and more of them. At the same time, the statistical office have limited resources, and it's typical in the statistical office that you have a fast turnover in staff. The IEA has done a couple of things to make it easier for people who sit around the world to collect data. We have published an energy statistics manual, and we even translated it into 10 languages. And it's widely used around the world. It's a good introduction to energy statistics, and it's a good tool to have close to you on the desk when you need to look something up. It's available in hard copy and it's available in a PDF.
Thank you, Klaus. For those of you who just joined recently, I just have seen some questions coming up that we covered at the beginning. I just wanted to confirm again that these slides and the recording will be made available after the event. And also just to remind those of you who have recently joined that if you want to ask us any questions at any point, there is a chat option in the right-hand panel of your screen. Please ask us any questions. We will be answering all questions in the interactive session after the presentation, but if you have something specific to a particular slide, please don't hesitate. So, following that introduction, we're also now going to move on to some basic concepts in energy statistics. I will start with the supply and demand breakdown and also go over some of the basic conversions. It may be quite elementary at times, but I think it's always important to cover these points for all people, even as just a reminder. Then Klaus will take you through some of the more complicated issues of calorific values and weighted average. So, to start off, I just wanted to very briefly summarize the differences between primary and secondary energy commodities. It can seem like quite an obvious issue, but it's something that needs to be covered. Energy commodities that are either extracted or captured, these are the most important words to note here. Those extracted or captured directly from natural resources are what we call primary commodities. The main examples of these can include crude oil, hard coal, and natural gas. Of course, this list is not exhaustive. The physical and chemical characteristics of the energy in this situation are not changed. Energy commodities that are produced from primary commodities undergoing what we call a transformation process are contrarily called secondary commodities. Petroleum products produced from crude oil or coke oven coke from coking coal are examples of this. For secondary energy, the important distinguishing characteristic here is the process of transformation. Transformation is any process transforming one form of energy to another. Energy of fossil fuels, solar radiation, or nuclear fuels, which are all primary, can be converted into other energy forms such as electricity and heat that can be more useful to us in this form. Energy that has been subjected to human-made transformation is secondary. So here we are looking at, this information is important when we're looking here at the supply and demand breakdown. The slide here shows the main commodity flows from the supply and the demand side, as you can see here. When presenting energy commodity data, arguably the most common format is the balance between the sources of supply and its use, which here is the demand. The main concept here is that of a consolidated balance, in that we calculate the difference between what is going in and what is going out. The difference between the two sums can indicate an imbalance. In terms of energy, this difference is called the statistical difference. Where the balance equals zero, issues can arise due to accusations of inaccuracy. It is rare that the balance would be perfect. This is what we mean. Therefore, normally what we are looking for here is a difference of no more than 5% either way, plus or minus, of the final number. If the result is any more than 5%, however, we would need, or any less, we would need to look again at the statistics, as the inconsistencies in these situations would be too high. Therefore, of course, the margin is very tight. As you will also see, the supply side has very few agents compared to those on the demand side. This can lead to more accuracy on the supply side than the demand side, of course, because there are less items to be monitoring. One additional aspect here is also to note is that the supply side normally requires a license in order to operate. Those actors involved require a license. Whereas the demand side has few to no restrictions, and therefore anyone can be involved in the data giving and monitoring process. This can impede on the accuracy of the processes.
Okay, thank you, Lucy. I think we got a couple of questions been answered by the people who are listening. And one question is electricity a secondary energy product? And that's a good question. Electricity is usually what we call a secondary energy product because it is not a thing. You don't have electricity in the nature. You have sometimes when it's thunder, then you have electricity. But electricity is usually produced based on burning of fossil fuels, or, for example, in hydropower, that you have a potential energy that's transformed into electricity, or solar power that's transformed into electricity. And another question that was asked is LPG, liquefied petroleum gas, is that a primary or secondary energy product? And LPG is the output of a refinery, and the refining process is actually one of the best examples of transformation from primary energy, which is crude oil, NGLs, into secondary oil products, which LPG, gasoline, gas diesel oil is coming out. So both of these are considered secondary energy products. And then another question is, what are the possible sources of inaccuracies in calculating the difference? When you calculate the statistical difference, you come up here. The sources, I think actually the best thing you can say is that you have different sources. You have a supply side here, where, as Lucy said, you have few agents, you have few coal mines, you have few oil wells, you have few natural gas sources. It's not, you need a license also to export and import oil products and energy products in general. And so generally this supply side is well monitored, whereas we got on the demand side, we got, for example, a lot of residential users, for example, petrol. It's difficult to actually know exactly how much petrol has been bought. So data on the demand side are usually from a different source, and this can create statistical differences. We don't care about statistical differences of 1, 2, 3, 4, 5%. If it's getting up to 5%, we're starting to wonder a little bit, is there any sources that we haven't taken into consideration? And especially if we can see that consistently the statistical difference has the same sign, if it's always positive year after year, if it's always negative year after year, then maybe if it's because we have a consistently higher supply than demand, then maybe it's some of the demand that we don't catch in our surveys, and this can lead to a statistical difference. But there can be different also timing. It's difficult to have that it's actually all the surveys are looking at the calendar year.
Okay, thank you, Klaus. There's a few more questions coming in, but I'm going to go over the slide, the next part, and I think that should answer some of the questions. If we don't answer anything, please don't hesitate to just come back. What I wanted to do was to briefly go over some of the different elements here on the slide, those that may be a little bit less familiar to some of you. So we start with production. As you go, there's rarely other contribution from other sources. For example, here we have imports and exports. Important to note, many countries have no production of natural gas, for example, just one example of a fuel, and therefore rely solely on imports. Whereas others have a surplus, and therefore their economy relies heavily on exports. This is the case particularly for Norway or Qatar, just to give examples. As I noticed that some people were asking about stock build and stock draw. This is also a terminology that can be unfamiliar. You'll notice also here that the arrows are pointing both ways. Stock change is mainly the difference in stocks from the opening day on the first day of the year, the opening stock levels, to the closing levels on the last day, on a national territory held by producers, importers, energy transformation industries, and large consumers. A stock build is usually shown as a negative number because it is when there is a smaller amount of stocks at the closing day than there were on their opening. On the other hand, stock draw is usually a positive number and represents when there is a higher number of stocks on the closing day of the year than there were on the opening. There's also to note here the point of international marine and aviation bunkers. These data are important, crucial to the monitoring process, as they can be very large and refer to international consumption. These statistics are not included in the national CO2 emissions, normally because it refers to the fuel consumed on an international space. As we move on to more the demand side, and we come back here, this is why I mainly explain to you all the difference between a secondary and a primary commodity, such as electricity production and the refining of oil products, which is the case here in transformation, and that's how we come to these different forms of energy. Here, when we mention energy sector, we're referring to commodities used to support activities within the fuel extraction, conversion, or energy production plant. These do not enter the transformation process. Of course, losses, there is the evident fact here, but there's also an important point to note in the monitoring of losses, and that is to consider theft, as this can pose a significant problem for many nations. The total final energy consumption represents where the energy is actually consumed by the end users. This, of course, brings us back to the beginning of the webinar when we discussed the micro-level users of energy data. This can of course cover industry, transport, residential and commercial, and non-energy use.
Okay, so there's a question, are losses in the supply side considered at all? Well, if you think of losses as some kind of spillage from like a truck that has petrol products, then it's actually here on the demand side. Although I do see that if you, for example, have losses in the production, like for example flaring of natural gas, that is usually considered before the marketed production. So some of the losses on the supply side are actually not counted at all, whereas most losses should be on the demand side. Which one? Non-energy use. Quite a few people ask about non-energy use, and the main part of non-energy use is the petrochemical sector that uses oil products to produce plastic and fertilizers. There's also oil products that are used as lubricants, and oil products like spirit that is used for thinners, for paint, and things like that. Well, and somebody asked, what is the definition of transformation? Once again, the definition of transformation is that you take a primary product, like thing you can find out in the nature, and then you transform it into things that you don't find in the nature, like, and that is mainly like heat, electricity, coke oven coke, oil products like diesel, gasoline, LPG, things that are easier for the end user to use.
Okay, if there are any more questions about the supply and demand breakdown, there's a few coming in. We're just there with us a few seconds. We'll just take into consideration some of the questions you're asking on this slide. I know it can be a little bit difficult to understand.
So we just take the two. There's one here that one asks, electricity transmission losses, are they included in demand side losses? Yes. And there's also one thing Lucy mentioned, like theft from the grid. It can be quite a problem in some countries. People hook up on the net and they just take electricity, considered as losses. Small solar power or wind power items, are they accounted for? Yes. In general, all energy is accounted for, but you are touching upon one of the weak points, maybe if you're looking at microgrids, places where you use a solar panel to give electricity to a small group of houses, maybe 2 or 3 houses. Things like this that in theory it should be accounted for, but I mean in some remote areas it's almost impossible to collect this. There's a question about statistical difference. One of the problems about statistical difference is that it basically shows something about the quality. And if you have a big statistical difference, it means that you have some things that are not accounted for in your statistics. And if you have 0, then it's most likely, because this doesn't happen. I mean, you always have a small statistical difference when you put sources together. Either it's because it comes from one side, or it's because you basically forced it to be 0. And some ask if it's always negative or always positive. You can't say it's always negative or always positive. But if it remains with the same sign throughout a longer period, it's usually because some things are not wrong. It should oscillate around 0 and not be larger than 5% of the final consumption. Yeah, I think we move on. There's a lot of questions. Some of them are very specific, and others are sort of a little bit difficult to explain right here. So I think Lucy will just move on with her presentation.
We'll come back to the questions, as I said, after we move on from at the end of the slide. So to actually just finalize what we've been saying, here is actually an example from France, a balance of natural gas. As you'll be able to see here, recognize it may help to actually understand some of the different elements that we were discussing here. As you can see, France has a very small production of natural gas, which is shown in the first column, and therefore relies heavily on imports from other countries, which is shown in the third line down. In looking towards the demand side, we can see here that natural gas is consumed mainly within what's deemed as other sectors, which was referring mainly here to household use and some to commercial, mainly here household. This is an interesting example. I think it can help to really understand what we were discussing in the previous slide. Those of you who wish to see more on this, the IEA, the Eurostat manual, can provide further information. Also, in week 4 of the webinar, Roberta Quadrelli will be going through an introduction to balances, and that will be able to provide further information. But please do keep your questions coming if you have them. So, having understood this, we're going to move on to some basic conversions. I won't take very long through this because I think the more complicated will be when Klaus comes to discuss calorific values. Here really it is to just go through what there are many different units of measurement that we may encounter in energy statistics. Especially that might be the case as well given the amount of different countries that you're all coming from. I think the last time we saw there were 73 countries represented within this webinar, which is absolutely fantastic. It means it's difficult to sometimes have one solid unit to really discuss. The one good thing about the basic conversions is that here we can group them normally into mass, volume, and energy. And converting between the same quantities here can be, well, let's call it easier than what's coming, in the respect that there's always a constant that helps us move from one to the other. So here's to provide you with some of the most familiar ones, as it were. Here in mass, we have kiloton equaling 1,000 tons, and 1 kiloton equaling 1 million kilograms. Down to volume, 1 barrel is let's say it's equivalent to 159 liters. These are not things that you have to necessarily memorize, but they're always useful to have. I'll show you in a minute to make your life a little bit easier. And 1 gigawatt hour here, for example, is 3.6 terajoules. One important thing, maybe the most important thing we'll give you today, is the link here to the unit converter. Take a little bit of time to come up on your screen. I'm sorry for that, please bear with us. But basically, this is available on the IEA website. This will help you to move from different conversions, different units easily. It's always good to memorize some of the points, but this should make life a little bit more simple. So just to give you an example here of how we mean from moving from one unit to the other, I'll give you a very basic example of converting 5 kiloton of oil equivalent to gigawatt hours. Remember from our last slide, the 1 gigawatt hour is equivalent to 3.6 terajoules, and 1 kTOE is equivalent to 41.868 terajoules. Therefore, in this respect, we will need to take 5 kTOE, which is times 41.868 terajoules per kTOE, equaling 209.34 terajoules. This is not mathematics from the head. Of course, calculators does come in handy. And then from that, we can do the 209.34 terajoules divided by 3.6 terajoules per gigawatt hour, giving us the final answer of 58.15.
Excellent. Now we go on, and we're halfway through. We will launch a little quiz for you to see if you are still awake. The question is, imagine you're stranded on a deserted island in the polar sea. You can bring 1 ton of a fuel. Which one would you bring? Would you bring a ton of coal? And if you are a coal nerd and you want to know what kind of coal it is, it's anthracite in this case, or a ton of diesel oil, or a ton of firewood. So make your choices, and we will give you the results in just a few moments. So how many have voted? 40. So we're still having people voting.
Okay, just 4 seconds left, and we'll close the poll. Okay, we're going to close the poll now. Thank you very much for voting.
So, if you want to stay warm for the longest time, you should take diesel oil. And quite a few of you agree on this. 47% of you said diesel oil, 30% said a ton of firewood, and 23% a ton of coal. The thing is, to get the equivalent of a ton of diesel oil, you would need 1,600 kilos of coal, but you would need even more firewood, actually 3 times as much, depending on what kind of wood it is and how dry it is. The lesson learned is that it's not good to compare mass figures if fuels are very different in the nature. So let's try to convert it into energy content, and let's have a look at calorific values to do that. Majority of data are collected in physical units. For example, you have tons of coal imported, liters of petrol sold, cubic meters of gas sold. But like we just saw in the quiz, it's difficult to compare mass and volume figures because energy content differ. Imagine you as a politician want to find out how many cubic meters of natural gas is needed to substitute coal imports. The answer methodologically is to convert all mass data and volume data to energy units. There are many energy units: joule, kilowatt hours, British thermal units, coal equivalents. In the IEA, we use oil equivalents. This is what Lucy used before in her example. And there's a historical reason for this. The IEA was established right after the first oil crisis in the early 70s, and it evolved around oil as the most important fuel. Well, the world was different at that time, but it means that we are still using oil equivalents as our main energy unit here in the IEA. Lucy just showed us how to convert within a family of units, from one mass unit to another mass unit, from one volume unit like gallons to another volume unit like liters. To convert from mass units into other physical units to energy units is more complicated. There's no constant factor to convert it, as it depends on the product and the quality. This conversion factor is called a calorific value, and it represents the heat obtained when the fuel is combusted. Different products have different calorific values. Also, for the same product, the calorific value can vary significantly. And I just noticed that I forgot to click on this one. So now here, as a big surprise, you can look at the calorific values. And what I wanted to show you here is that for bituminous coal, calorific values can be very different. For example, in Kazakhstan, it's around 19,000 kilojoules per kilo, whereas in New Zealand, bituminous coal can be up to 28,000 kilojoules per kilo. It's quite important to remember this, and but it's also important to remember that there are some definitions that bituminous coal is always within a range of calorific values, because if it's not within this range, then it's simply not bituminous coal, then it's another kind of coal, like subbituminous coal. So it's very important that you have good calorific values when you make your energy data and when you convert from physical units to energy units. It's also important to know that we usually deal with two different kind of calorific values. We deal with the gross calorific value, the GCV, and the net calorific value, which is also called the NCV. As it's in the name, the gross calorific value is higher than the net calorific value, but what is the difference actually? When you combust the fuel, when you burn fuel, there's also some water that vaporizes, but this can rarely be used for energy purposes. Basically, as a chemical process, when you burn coal, some of it just disappears into the air as water vapor. It's not the same as losses, or it's not the same as transformation losses. It's just something that in the chemical process comes out as water or steam. And then you have left the useful heat. Luckily, most of the heat that is produced is useful heat. For natural gas, the net calorific value is 90% of the gross calorific value. For oil, it's around 95% of the gross calorific value, and the same for coal. Let's have a little example here on how to calculate the calorific or the energy content of a physical value. Imagine that a country produces 2 billion cubic meters of natural gas. The calorific value, the gross calorific value, is 38,000 kilojoules per cubic meter. What is the gross energy content? Well, first we need to convert the gross calorific value to a more convenient unit, and so we convert it from kilojoule per cubic meter into terajoule per billion cubic meter. Then we can easily just multiply the 2 billion cubic meter with the 38,000 terajoules that we have per billion cubic meter. That gives us 76,000 terajoules. And that's the gross energy content. Or it gives us, if we look at the net energy content, we take 90% of this and we end up with 68,400 terajoules. This is math, and it's good to know. Lucy and I have been training for many times, and always when we do these training weeks, it's the same problems that come the whole time. Going from one unit to another, you can make big mistakes, and going from physical units to energy units is always a big problem. And even though we have usually this session in the beginning of the training, people have different problems with it throughout the week. Let's move on to the next slide. Something about, okay, we have a question here. Okay, so there's a question on why you have different calorific values in Kazakhstan and New Zealand, and quite frankly, I don't know. It's just something that happens underground. These fossil fuels, they have a different structure. It might have been something to do with how deep it is, how much down into the earth you have to go to get it. I don't think you can say that in some regions they have similar characteristics, but it's not something you can really do anything about. It has the calorific value it has. The next, there's another question, is how do you deal with when the calorific value of oil products change? Luckily for oil products, calorific values don't change that much. The quality of like a liter of diesel oil is pretty much the same from year to year. But you do have, for example, crude oils can change. You can have, for example, 1 year it's got one calorific value, and natural gas can also change from year to year. So if you want to make good statistics, you do need to apply specific annual calorific value for each year. So it's actually specific for each year. Moving on to this, what do you do if there are more than one coal mine in a country, or the crude oil is produced in 2 or more oil wells with different crude qualities. In most cases, a country has more than one coal mine, and it's not the same. So we need to take into consideration when we give the calorific value. Look here, for example, we have in the first example here, a country has 2 coal mines, A and B. They produce the same quantity, 100 kilotons of each. One has a calorific value of 25,000, the other one has 20,000, and the calorific value for the whole country is pretty simple. We just take an arithmetic average of this. But what if the quantities produced in the 2 mines are not the same? If, for example, in mine A you produce 400. If you produce 400 kilotons in one mine and 100 in the others. In this case, you need to take a weighted average. And a weighted average is about that most of the coal is in the higher quality mine, and this has to be reflected in the average net calorific value. So you apply this formula, and what is important to see here is that it's weighted according to how big the production is in A and how big the production is in B. And this is how you do make a weighted average. In this specific example, you see you have the calorific value here of the mine with the big production of 400 kilotons is here, and the calorific value of the smaller mine with the lower quality here is here, and it's weighted according to how big the mines are. Here we have the weight here, and we divide by the total amount. And we end up with a calorific value of 24,000 kilojoules per kilo.
Okay, that brings us to the end. We were a little bit ambitious with 30 minutes, but that brings us to the end to the slides that we wanted to go through today. We hope that this has been useful for you, and we hope we didn't go too much into some complexities. I know it got a little bit mathematical at times. We do have some questions that were left unanswered, and also we are opening up now for a more interactive session. We were lucky enough to be able to do some as we were going along, so I think some questions have been answered. There are a few here that we have. Please feel free to ask any of your questions now. We are dedicated. We're dedicating some time here to answer all of your questions. If you prefer to email your questions afterwards, that is absolutely fine as well.
Okay, there's one question here concerned with double counting on demand side, and let's go back to the slide. I think if I understand this question right, you are you who asked the question, let us know if that's not what you meant. The thing is that you have like a kind of transformation here. Some of it goes into transformation. And if you look at the whole economy, some coal, natural gas would be used in transformation, and the transformation would then be electricity, which would be used here. And in this case, you're absolutely right. There would be a double counting. This thing about double counting is taken into consideration when you make the energy balance, which will be dealt with in week 4 of this series of webinars. And it's actually very, I suggest you listen to that presentation, because it's very interesting to see how you, with one sheet with what's called the energy balance, how you can get a consolidated overview of an energy situation in a country. All right, let's move on. There's one question I like here: the tactics to adjust statistical difference between supply and demand. If you do all your due diligence and you make your demand side and your supply side, and you end up with a 10% statistical difference, then there are different, I would say that there are different strategies you can pursue. One thing is to ask yourself, take a logical or sensible approach, and then see, is it the supply side or is it the demand side? And if you have a supply side that's bigger than demand side, then it's probably because you're missing some consumption on demand side. That could be, for example, if you're looking at the supply side and demand side on fuels for transportation like diesel or petrol, and you see that supply side is larger than demand side. Maybe you have a border trade. Maybe you realize that the petrol in the neighboring countries is much more expensive, and people go to your country to buy petrol. That could be something that is not picked up by the demand side. There's one question about ask us to elaborate on solar and wind on the supply-demand side. The thing is that solar and wind are a little bit, I don't know how you can say, they're a little bit difficult to deal with methodologically, because basically we consider solar power as a production, but we don't consider that when you use electricity in your home and it's based on solar power, we don't say that you consume solar power. We say that it's actually solar power is transformed into electricity. So you never have a demand side of solar power, and the same with wind and the same with hydro. All these are transformed into electricity. We call it domestic supply, even though we include imports, because we want to look at what's available in the country for consumption. And so we take the production, take away the exports, and add the imports, and take away the international marine bunkers and aviation bunkers, because they're not exactly related to our country. They could be basically, because the energy is consumed in international air, international water, then it's not to do with our country. And we take the stock build or stock draw into consideration, and then we have what is used in, what we think is used in the supply in the country. On the demand side, it's we try to get more detailed information on how the energy is used, and that can be sometimes a little bit difficult, because as you can imagine with, for example, petrol, you don't know if it's a bus that's using the gasoline, or if it's a private car, if it's a moped, or it's sometimes quite difficult to get information on these end use. And then there's a question on which types of models does the IEA use to model supply and demand. Well, we have the IEA. We mainly rely on we are what you can call a secondary statistical producer. We don't collect data ourselves from users. We don't ask people how much electricity they use. We rely on reportings from countries, from member countries of the OECD or non-member countries. They compile the data, and we just elaborate them into our concepts and publish them together in a comparable format. There's a question here. Do you have energy efficiency rate of different sources from gross to net? Yes, I think we did tell you that. I think there was also another question on efficiency, like, for example, how much electricity do you get out if you use 1 ton of coal for electricity production. Those numbers we have some guidelines. We usually say that if you produce electricity from coal, then its efficiency is usually around 20, 30, 40%, depending on the technology that's used. For natural gas, which are usually newer technologies, efficiency is a bit higher. If it's combined heat and power generation, we expect efficiencies of up to 60, 70%. I have the rates somewhere, I don't remember them by heart for all products. How does electric vehicles fit in this model? Electric vehicles are, for example, on this one here, demand side, if you would have like Lucy showed us the product balance for natural gas, if you sort of try to imagine that this is the balance for electricity, then electricity consumed for electric vehicles would be down here in transportation sector, which is here on this model. Then there's another good question about conversion factors for CO2. We do convert all our energy data into CO2 emissions, and they are there's a separate book on that and a separate database. I think the CO2 emission factors are available in this publication. Okay, there's a question here on transformation of primary energy sources to electricity. Do you consider the technology used in their efficiency, for example, their efficiencies? Yes, we do take technologies into consideration. It's one of the ways that we check the data. When we put data together, we look at efficiencies, and we like to have them within a range. But we know, for example, if you have more than 100% efficiency, then it's because something is not right. Next Wednesday, next week, we have a webinar specifically dedicated to refinery checks and how to improve quality in the refinery check data. And the week after, we have a webinar combined on renewable energy and electricity, and this efficiencies in different technologies will be touched upon in this one. There's a good question here on electricity storage, for example, dams, electricity, electric car batteries. They're not accounted for in the stock build. We don't consider them that important at the moment, considering that in the IEA we usually like to have 90 days of stocks of oil products, which means that if the supply of oil would fail one way or another, there will still be stocks at national level to cover 90 days of oil's use. An equivalent, I just heard the other day that the equivalent stock that we have for electricity is only 30 minutes. If there wouldn't be produced any electricity, after 30 minutes there wouldn't be any electricity left because of the storage problems with electricity. Losses on electricity is usually, there's a question here, and it is whether losses are just a generic factor or whatever it is. We use losses for electricity. We usually get them from the electricity distributors. They know how much they put into the net, and they know how much is billed. Whatever the difference is usually because of distribution losses or because of theft, and we get those numbers directly from the electricity providers. Oh, let's take one. There's a good question here. Whether there can be significant differences between the data provided by the country and the data that could have been collected by the IEA primarily in terms of data collection methodology. And there's the IEA, we make energy statistics for the whole world, 150 countries, so there are still some countries that we don't cover, but for most of the world. And we usually take a country's energy data, and if it's not done according to the IEA methodology, we transform it into another, we transform it into our methodology. And at the same time, there are other, like the IEA, we usually cover the OECD, but in, for example, in South America, there's the OLADE, they make their own energy statistics. Unfortunately, definitions are not exactly the same. We do work very closely together with the other international organizations like the UN, FAO, IRENA, which is like the International Renewable Energy Agency, and to make sure that to get the definitions closer to each other. It's something that takes a long time, but we've been working on it for many years and we've made significant progress. There's still room for improvements in the future, but yes, there could be differences. Okay, there's a question here whether the question sounds like this. It seems that the current method mainly accommodates conventional fossil fuels. Would it not be better to specify even household production of heating and electricity from, for example, solar was accounted for on the supply side? I think that's a good question. I don't think I can answer it. I think that that this is some of the things that because we're currently working a little bit on improving our definitions and improving our methodology, because a lot of this way the statistics have been collected is historically, and this boom that you see in renewables right now is something that we don't take into account. Yeah, I think for some of the fuels it doesn't matter that much. I think if it's converted into electricity, then you still have in the energy balance, which you will see in week 4, you will see that you can calculate the renewable share of the total primary energy that's supplied to a country. So you do take the renewable into consideration, and the end use, whether it's made on wind, solar, hydro, or fossil fuels, doesn't matter so much in my opinion. Yeah, another question here. Going from renewables to nuclear, there's a question here whether nuclear is included in the energy balance. Yes, it is. It is included, and it is treated basically the same way as we treat hydropower and solar and wind. That we take the electricity, and in the supply side, we have a supply data on the nuclear like we have on renewables, and then it's transformed from nuclear into electricity on the demand side. Yeah, there's a question here, what does the IEA do when they cannot get one of the variables of the model for a specific country? For example, if the country doesn't want to share the data, or if it's not measured in the first place. Well, we would usually try to estimate it. We have different ways of estimating things. If it's something that is usually if we have it one year and we don't have it the next year, we could use a growth rate, for example, GDP or population. Or we could use, for example, using a share. If we don't have, for example, the electricity that's produced on coal, then we would see how much coal is used for electricity, and then kind of estimate that based on an efficiency to see how much electricity output there is.
Okay, thank you very much for all your questions coming in. We hope that you've enjoyed this webinar. We know that there's still some questions coming in. As we explained at the beginning, there is a time constraint on the webinar. We will work through the questions that have come in that we've been unable to answer. There's still some questions coming in about the slides being available. Yes, the slides and the presentation will be made available by early next week. And I saw actually some questions coming in French. Normally the transcript as well of this particular webinar will be translated into French, so that should be helpful in that case. The questions that have come in that we've not answered, as I said, we will get back to you, we will answer them, and certain questions that were better directed to some other experts across the agency, we will ensure that you get the correct answer. We really hope that you've enjoyed it. We hope to see you all next week. Next week it will be my colleagues Marcus and Jan who will be taking you through the refinery balances. They're experts in that area. Please don't forget to register. If you have any comments on the webinar or anything else, please we'll leave this open for a few minutes. Please give us any feedback, and also feel free to email me at any time. Thank you very much for taking the time to join us today, and I look forward to next week.
Yeah, thank you very much, guys.
Thank you.